So now that we have learned about the different forces acting on a gravity dam and how to calculate them, so now we can talk about the different modes of failure and how those forces are going to affect the stability of a gravity dam. So when it comes to modes of failure, there are four principal modes, uh, major ways in which a gravity dam can fail. So the first one is called overturning, and overturning is, suppose you have some object like this. If you push it, then it will fall like this. So that's overturning. And in case of a gravity dam also, we have force of water from this side, and that is likely to overturn this whole dam like this. And this overturning is generally assumed about the toe of the dam. So this is one mode of failure. Then sliding is quite obvious. It is when the whole dam slides along the surface, along the river bed. Then it is called sliding failure. Then tensile stress development. We are not talking about tensile failure directly, but tensile stress development itself is assumed or considered as a failure of the gravity dam, and that's because we have to be quite conservative in design, and therefore we assume that the concrete or the masonry that is used to build the gravity dam has zero tensile strength. And therefore anywhere in the dam, if tensile stress develops, then we'll consider that as failure of the dam. Then on the other side, the excessive compression or compressive stress, if that develops and if it exceeds the allowable compressive stress, in that case also the material will crush and the dam will fail. So we'll see these modes of failures one by one now. So the first one is overturning, and as we've discussed, it is caused by the forces which create a moment about the toe of the dam. It tries to topple it over to the downstream direction. So in this case, if we look at all the forces that we have learned about, the hydrostatic pressure force, which is this force, that is going to overturn the dam, and that's because if you take the moment of this force about the toe, then you'll see that the direction of this moment will be in this direction. Then the uplift pressure, if you consider the moment due to the uplift pressure about the toe again, then also the moment will be again in the same direction, that will be towards that will be contributing towards overturning. It will try to overturn the structure. In addition, forces of silt, if silt is deposited at this point, then it is also going to exert some pressure in this direction. So if you consider the moment about the toe again, then also it will be an overturning moment. Then earthquake, the earthquake force may act in different directions. It may act in this direction, it may act in this direction, and it may also act sometimes in the vertically upward or downward direction. So depending on what direction it is, it may cause overturning. Then wind, only if wind is blowing in this direction, then it will be adding to overturning. Then wave and ice forces, so if wave is generated here, then it is going to give some additional pressure and that is again going to be adding to the overturning. Then ice also, the ice, the force due to ice may be either due to impact of ice blocks on the dam or due to formation of ice sheets by freezing of the water surface, which will try to expand the water surface and that will exert a push on the dam. So all these forces will be causing the overturning about this toe point. Then, while some forces are trying to overturn the dam, there are some forces which will be trying to resist that overturning. So the first one is its own weight, that is the self weight, and the self weight, if you take the moment of this self weight, that is this white arrow, about this toe, then you will see that the moment because of this will be in the opposite direction. The overturning moments were all in this direction. In our diagram, it is clockwise, and the resisting moments are in anti-clockwise direction. So that is one resisting moment, one force that is causing resistance, that is giving resistance to the overturning. Then if there is tailwater pressure, if there is tailwater, that means there is some depth of water in the downstream of the river, downstream of the dam, then that is also going to give some resistance against overturning, because if you consider this toe, then the line of action of this hydrostatic pressure will be having this distance, and that will also give us a moment in this direction which is resisting the overturning. Then some other forces will be, so these two forces will be trying to stabilize the dam. In addition, if we also provide, suppose this inclined surface of the dam in the upstream, it may be like this or it may be near the bottom also, but whatever it is, we'll have to consider. And if that is done, then we'll also have to consider the water weight right above this inclined surface, because that will be acting in vertically downward direction. So we'll have to consider, suppose this is the inclined part, and then we'll have to consider the weight of this portion of water. So this volume of water we'll have to find out, and again this weight will be acting in this direction, and because of that we'll have again a resisting moment. Similarly, this triangular portion of water will also be acting at somewhere around here, which is a very small force, and the distance itself is very small when you measure it from the toe. Suppose this is the point, this is the toe, and this is the line of action of this vertical weight of this small amount of water, then we'll have a small moment like this. So all these forces will be trying to resist that overturning. So it is basically resisted by self weight, hydrostatic pressure of tailwater, and the vertical component of upstream hydrostatic pressure if the upstream dam is upstream dam surface is inclined. If it is vertical, then this portion will not be there. So to make a dam stable against overturning, the main criteria is that it has the resisting moment must be greater than the overturning moment, and the overturning is assumed to occur about the toe. We already discussed that. So now we know how these overturning moments will come about, and we'll try to calculate them. So the overturning moment, let's call it MO, and that will be the sum of the moments of all the forces that are trying to overturn the dam. The first one is the hydrostatic pressure in this direction. So the hydrostatic pressure force, which we calculated earlier, we gave it the notation Fh, and the distance of this force about the toe will be, we can find out just by finding out the distance of its line of action from this point, and that will be, we know that this force will be acting at distance 2/3 of h or 1/3 of h from the bottom or 2/3 of h from the top. In this case, we need the distance from the bottom, which is the level of the toe itself. So this distance is 1/3 of h. So we'll multiply this hydrostatic pressure force with its distance from the toe, which is h by 3. Then the uplift pressure force. The uplift pressure force, we know that it will be a distribution like this, where this value will be equal to capital H rho g, and this value will be small h rho g, where small h is the tailwater depth. So, and in between it will be varying linearly. So we need to find out the total magnitude of this entire pressure force, and also need to find out the distance of this resultant force from the toe. That means if the resultant is acting somewhere here, then we'll need to find out this distance and then multiply it with the distance. So if you want, you can find out the total force by taking area of this diagram, this trapezium, or you can also divide this into a triangle and rectangle. So this part is the rectangular part and this part is the triangular part. I do not remember the centroidal distance formula for trapezoids, so I'll take the easy way, which is dividing it into a rectangle and a triangle. So let's call it FU rectangle, which is this portion, and the area of that will be equal to this FU rectangle, and the distance of this entire force because of this distributed pressure will be, the resultant will be acting right at the middle here. So its distance from the toe will obviously be B by 2, where B is the total width of the dam, total base width of the dam. Then for the triangular part, we'll take the force Fu triangle and we'll multiply that with the distance, which will be, because it's triangle, it will be acting at a distance 2/3 of B from the toe. So 2/3 of B. If you want, you can write the expressions for these forces Fh and Fu. So if you write the formulas, then this will become, we'll get this kind of an expression. And here you see the terms within these yellow brackets are the distances of the forces from the toe, and the other terms, so all these terms which are within these green boxes, they are the forces. So we are basically calculating the moments due to all these different forces. And always remember one thing, while we are calculating these forces, we are always calculating on per unit length of the dam basis. So if this is, suppose, a unit length of the dam, then the uplift pressure, which is suppose acting on the bottom surface of the dam, the bottom surface itself will be having an area equal to, suppose, length, the width of the dam is B, and we are considering unit length, therefore B into 1, that is B only. And therefore in the uplift pressure calculation for this, suppose, rectangular portion, we took the pressure, which is rho g into small h, we multiplied that with the area of the bottom area of the dam, which is B into 1 or simply B. Similarly, in case of this one and this one. So this is how we'll calculate the overturning moment. Then we'll have to calculate the resisting moment against overturning. So while calculating resisting moment, we'll see what are the forces that are causing it, that are giving resistance to this overturning. The first one is the self weight, but to find out the self weight, this particular geometry may be difficult to find out, difficult to use while we are talking about the distances of forces and the forces themselves. So therefore we'll divide it into these three simple geometrical portions: one small triangle, one rectangle, and a bigger triangle. So we'll give them names, and these names will be, suppose, W1. W1 will be, at the same time we are also trying to see where these forces will act. So W1 will be acting here, and its distance from the toe will be this entire distance plus this distance, and this distance we know that it will be 1/3 of this width of this small triangular portion. So the width of the dam we are also going to divide into convenient parts, that is this one, and this one. So let's call them B1, B2 and B3. So W1 will be acting at a distance B3 plus B2 plus this small portion of B1, which is 1/3 of B1. So the resisting moment MR, let's call it, will be sum of the moments of all the resisting forces. So the first one is W1 multiplied by the distance, which will be B1 by 3 plus B2 plus B3. Then we'll also talk about the other two forces or other two components of self weight. The middle portion will be acting right at the midsection of this rectangle, which is W2, and this bigger triangular portion will be the weight of this bigger triangular portion will be W3 and will be acting at a distance from the toe, which will be 2/3 of this B3. So we'll again write them one by one. W1 is done, then plus W2 multiplied by the distance will be B3 plus half of B2. So B2 by 2 plus B3. And for the last portion, W3, the distance is simply 2/3 of B3. So this is how we are going to calculate the resisting moment because of the self-weight components. But there are some other forces as well we have discussed. If the dam surface is, the upstream dam surface is inclined, then we will have to calculate this weight of this wedge of water, this volume of water, and depends on what portion of this dam surface is inclined. It may be a triangular volume, and in this particular diagram it is a trapezium, and we can again divide it into a rectangle and a triangle. So let's again call this, suppose, V1 and V2, and I'm not going to explain too much about the distances. We'll simply write the expression. So plus V1, let's suppose V1 is the weight of the rectangular portion of this water, then V1 multiplied by the distance will be B1 by 2 plus B2 plus B3. Now you'll just think for a minute how this distance is calculated. Then V2 multiplied by 2/3 of B1 plus B2 plus B3. So this is about this volume of water, and on the downstream side also we have this small volume, and that is the depth of this tail water is going to exert some hydrostatic pressure in the horizontal direction, and the weight of this triangular volume is going to act in the downward direction. So both of these two forces will be resisting the overturning, although to a very small extent, but still we are going to add them. So the hydrostatic pressure will be rho g into small h, which is the pressure. Then the pressure force because of that will be, we can calculate it as half rho g h squared. Then we'll have to multiply it with small h by 3, because that's the distance of this hydrostatic pressure, this horizontal hydrostatic pressure from the toe. It's a very small distance. H itself was very small, and this distance will be h by 3. And the vertical force will be acting at a, we'll write down. So let's call that V3. I think in the previous lecture we called this term as F small h, if you remember. Please check if the notation is correct. So then this force, let's call it V3. Then the distance of this V3 from the toe will be 1/3 of here we'll have to calculate the distance in a different way. So suppose this is the dam near the toe, which is like this. Then we have water. This height is h. Then to find out the volume of this portion of water, this triangular portion of water, we'll have to know about this slope of this downstream surface. And from that, I'm not going to discuss this because it is simply some geometrical problem. So whatever that distance is, this is V3 suppose, and this small distance, let's call it suppose D3. Sorry, suppose this distance, we are calling it D3, then it will be 1/3 of D3. So this is these are the forces and their moments which will be resisting the overturning. So after we calculate the overturning moment and the resisting moment, again in the resisting moment, just for the clarity, I'm going to mark the distances in yellow brackets, and the remaining parts will be the forces. So all these yellow bracketed portions are the distances of those forces from the toe, and the parts highlighted by green are the forces themselves. So this is how we calculate these overturning and resisting moments. Once we calculate them, calculate these moments, one thing we have to do is check whether the resisting moment is greater than the overturning moment, because only then the dam will be stable. So what we'll do is we'll find out something called a factor of safety. So factor of safety against overturning will be given by the resisting moment divided by the overturning moment. And because the resisting moment must be greater than the overturning moment for stability of the dam. Therefore, this factor of safety must be greater than 1. And how much greater, that will sometimes be governed by some kind of IS code, some other guidelines, or maybe decided by the engineers. So 1.5, sometimes 1.3, sometimes even 2. It depends on, you can find out while you are suppose designing a dam what is the required factor of safety, and you'll have to design the dimensions of the dam based on that factor of safety. So this is how we analyze the safety or the stability against overturning.